Dijkstra's algorithm. Dijkstra's algorithm is an algorithm for finding the shortest path between nodes in a graph. The graph may represent, for example, a road network, and the algorithm can be used in the GPS system. In 1959, Edgar Dijkstra, a Dutch computer scientist, invented a systematic method for finding the shortest path that became known as Dijkstra's algorithm. The notation for this algorithm goes like C x y, meaning link cost from node x to y. It is equal to infinity if not direct neighbors. dv, current value of cost of path from source to destination. pv, predecessor node along path from source to v. And prime, set of nodes whose least cost path definitely known. Here's an example of using Dijkstra's algorithm using a graph and a table. Apply Dijkstra's algorithm to find the shortest path from node A to all the other nodes. Step 0. We start at node A, so n prime is equal to A. Next column tells us what nodes we haven't reached yet. They are B, C, D, E, F. Next column is node B. It takes 3 units to get to node B, and the predecessor is node A. So DB is 3 and PB is A. Next column is node C. It takes 2 units to get to node C, and the predecessor is still node A. So DC is 2 and PC is A. Next column is node D. We can't reach node D from node A, so we put in infinity. We can't reach node E and node F either, so we put in infinity for the last 2 rows as well. Step 1. We highlight the shortest path. The shortest path goes through node C. Therefore, we add C to the column of the reached nodes. Now n prime is equal to A and C. We still haven't reached B, D, E, F. Shortest way to reach node B is through A. So DB is 3. PB is A. We ignore node C since we already know the shortest distance to reach it from A. We still can get to node D because we've only reached nodes A and C, and there is no straight path to D from A or C. We put in infinity. Node E is reached through C, and the shortest distance is 4, so DE is 4 and PE is C. We can't reach F, so we put in infinity. Step 2. We highlight node B because it's the shortest path. We add B to n prime column. The nodes that we haven't visited are D, E, F. We ignore nodes B and C since we know their shortest path already. Shortest path to reach node D is through node B, which adds up to 6 units. So DD is 6 and PD is B. Shortest way to reach E is going through C, which adds up to 4 units. We can't reach node F through nodes A, C, B, so we put infinity. Step 3. We highlight node E for its shortest path. We add E to n' column. D and F are yet to be visited. Shortest distance to get to node D is 6, and you go through B. To get to F, you'd need to go through E and C, which adds up to 8. So DF is 8, and the predecessor of PF is E. Step 4. We highlight D for its shortest path. We add D to n' column. We haven't reached node F. To get to F, we go from A to C to E and then get to D. It adds up to 8. The predecessor is E. The table is complete. Here is the pseudocode for Dijkstra's algorithm. This is a C++ program that implements the example described in the report. We define 9 vertices, a function that finds the minimum distance, function that prints the distance, function that implements Dijkstra's algorithm, and in the main we have two-dimensional array that defines the graph. We run the program and here's the output. The source file is turned in with the report. Here we have 3 animations that illustrate Dijkstra's algorithm. Beyond the linked state routing algorithm and Dijkstra's algorithm in general, there also exists another technique for finding the shortest path through a graph. This algorithm, called the Bellman-Ford algorithm, can be used in the same way that Dijkstra's algorithm can be used to allow routers to determine optimal path through a network, and is implemented in a class of routing protocols called distance vector routing protocols. Distance vector routing protocols are utilized in intra-network routing much the same way that linked state routing protocols are. Both approaches to routing use the concept of path cost and model the network of interconnected devices as a graph, with the routers representing the vertices or nodes and the connections between them representing the edges which connect these nodes. The report gets into details of Bellman-Ford and distance vector algorithm. Here's our Bellman 4 distance vector routing simulator that we wrote using Python. All of the files will be included in the project folder. Here's the demo of the program. Thank you for watching.